You're testing value. I swear to God, I'm gonna stab you with something. Professor, there's about to be violence in this class right now, so.
What's that?
There's about to be violence in this class right now.
Oh my
Tell
God.
him, don't do it. Take your cheating test out of here. I'm telling you, Professor, check him next time. Metal detector, I was just saying. He's either a really good guesser, which he's not, or, you know, can't guess something.
I thought you said.
I know, but if I was the
I'm not, Professor, look, how about this? I'll say it another way. I'm not saying he cheated, but I don't think he deserves that grade. I'm just saying. There you go.
All right, let's get started here. Let's go through the exam problems now. And I'm just going to solve these. We'll solve these together. So implement this function are identical. So we pass in references to two vectors A and B. Notice they're declared const. Well, that doesn't matter too much. But it means that the function doesn't modify A or B. It just examines the state of A and B. All right, so we need to return, this is called a predicate function. It returns true or false. So we declare the return value as bool. And we need to see of each value in A equals each corresponding value in B. So there'll be a comparison that looks like this. All right, that means that the, oh, sorry, thinking about something else. That's the condition that we want. But we want that to be true for all I that scans the valid indices of A and B. Now, in order for this to make sense, A and B should have the same size. So if they have different sizes, then they're not identical. So we'll check that first. So if A dot size equals B dot size, then we're okay. So we could do it like that. But it's simpler to check to see if they're different. If they're different, then we're all done in this. We can just return false. So it's easier to check that the sizes are different and then take a quick action, which is just to return false. So that's a better check. And it's similar to this. We need to check every pair, AI and BI, and see that they're equal. The simplest way to do it is to try to find a value where they're not equal. Try to find an I for which they are not equal. If they're not equal, then we return false. And after we've tried all values for I, then we know that they must all be equal. Then we can return true. Now what we need to do is put this expression inside of a loop. We need to let I range across all valid indices of A and B. Oops. There it is. Does that make sense? All right, what about this number 2? Implement a function that determines if the vector only contains the number 7. I think I put up some examples of this, didn't I? During the exam.
During the practice.
You did the 13. Yeah, that is unlucky.
Oh, I did. Didn't I put up,
No.
during the exam, I put up examples.
No, that was the binary search. You put up 8x and this way, x that way.
No, you did. So,
Oh, yeah.
Oh yeah.
Didn't I do something like that?
Season.
So, so the bottom one is an example. So 773 is an example where
Bless you.
it's not lucky because it's not all sevens.
Oh.
So basically, we have to make sure that everything is a 7. So I'll go like this. And this should be V. So we're going to scan across all values. And if we find a value that's not equal to a 7, then it's not lucky. Otherwise, it's lucky. And actually, this code is not, although I accept this, but it's not,
So that's no, because it says 100. Oh, okay.
actually, this is okay. So if the vector is empty, it returns true.
It's too
Yeah.
complicated.
I have a question. Would you still accept it the other way around? If bi equals 7, return true or return false?
All right, let's take a look at that. If vi equals 7, then return true. Well, we would return true for the second example right there, 773. Not every value is 7. So you're making a conclusion too early. You have to look at every value to see that every one is a 7.
That was only gonna check the first, once it gets to the first one that's a 7, then it exits the loop, right?
Yeah, and if you had an else, it's the same problem.
Oh,
Yeah, you're never getting to your second statement.
This will work if the vector is of size 1 and it only has a 7, but if it is of size 2 and it has a 7 and a 13, then it's not going to work. I think what you need to do is maybe throw in your mind as you're thinking and you want to check the validity of your code, you need to conjure some test cases and make hard test cases so that you try to break your code, try to find the flaw in the logic. That's why I spend a lot of time talking about and having you actually write test code. Because that's how you need to validate your logic when you come up with a solution. You should. And I gave you during the exam, I gave you those 2 test cases there to help you along. So, but you should be able to come up with those test cases on your own. All right, let's look at 3. Write test code that tests every statement in the isLucky function you implemented in the previous problem. Express your test using assertion. So we want to arrive at this return statement and this return statement. So we need to create test code that returns true and false. So we'll do it like this. This is not going to be the best test code. This is just going to be test code that executes every branch of logic. So we'll push back a 7. We'll assert that the function v is lucky. Then we'll push back a 3 and assert that it is lucky returns false. Maybe this is easier to look at. That's the same thing. One student used my test code exactly in the exam. That was a pretty safe way to go, actually. But to do that, you would push back, you'd have to create two vectors. Any questions about the test code? See, is lucky here we have the test code returning true and returning false. So we know that we're exercising every line of code in the program. That doesn't make it, that's called coverage. That's good coverage. It's still not a good test. It should do more testing, but just for the purposes of the exam, I wanted you to satisfy that one criterion, which is to have good coverage. A question? For those coming in late, your quiz papers are down here. You can come and get your papers. All right, let's look at number 4. Is strictly increasing. Write a predicate function called is strictly increasing that checks whether a vector of integers contains values that are in strictly increasing order. A declaration of the function is shown in figure 3. The function returns true if the elements are in strictly increasing order, otherwise it returns false. And then there's an example. This sequence of integers is not in strictly increasing order because there are two 6s next to each other. But this vector is okay. This is very much like the other problems. We need to check pairs of values. It's the second item in the pair bigger, strictly bigger than the first item in the pair. And if it is, then check the next pair. If the next pair fails on that criterion, then return false. We know that it's not strictly increasing. But if we check every pair, we don't find any problems. Then we can return true. I'm just going to copy this line up here. So let's check all the pairs. So we're going to check if we find a bad one. And if we don't find a bad one, a bad pair, then we'll return true. It is strictly increasing. So if we find a bad pair, we'll return false. It's not strictly increasing. So what does it mean for a pair to be bad? It's bad if
That the element before it is greater than or equal to 5 plus 1.
good.
And top clear, aren't you missing that size minus 1 right there?
Very good. Very good. So we can't go to the last element. We don't want the loop to run when I is at the very last position. Because if I is in the last position, then V of I plus 1 will be undefined. So this would be a logic error. So we need to let I reach that position which is 1 before the end. All right. What about number 5? Write a predicate function, so a function that returns true or false, a bool function, that checks whether two vectors are complements in the sense that their elements pairwise add to 0. For example, those two vectors are complements. If you look at the pairs, minus 2 and 2, they add to 0. 3 and minus 3 add to 0. 0 and 0 add to 0. Minus 7 and 7 add to 0. So those are called complements, according to this definition that I have in the problem statement. If the two vectors have different numbers of elements, then they are not comparable, so return false in this case. What's another loop problem? It's pretty much seems like the same pattern over and over again. It's all the same thing. Look at the similarity to the other problem. We need to find a bad pair. If we find a bad pair, we return false. Otherwise, all the pairs are good pairs. We return true. All of these problems seem to have this theme. Now here we're comparing A to B, so we want to go to the end of the vector A. So the pairs are, we're comparing A of I with B of I. Oh, but we have to check, for this to work, they have to have the same size. And in the problem statement itself, it says if the two vectors have different numbers of elements, they are not comparable. So return false in that case. So what goes here? This is the one thing we didn't do. So if they are complements, the definition of that is that the AI plus BI equals 0. So if AI plus BI does not equal 0, then we found our bad pair. We can return false. Otherwise, we have to try the next pair. After trying all pairs, we don't return false, then we return true. Count occurrences. So we implement the function count occurrences. The first argument of the function is a two-dimensional array of integers, and the second argument is an integer k. The function returns the number of times k occurs in A. Rows and columns are predefined constants. You don't have to define them, just use them. So we need to count the number of times k appears in this matrix. So we need a variable to keep track of the number of times we find k. So we'll need to range across all the valid indices of A, looking for k. Each time we find k, we increment our counter. So we have a counter set to 0. Just an integer variable. You can call it something else if you like. Now we need to look at every item in this two-dimensional array. So we'll let I range across all the indices for the rows. We'll let J range across all of the indices for the columns. And at the very end, we return the counter. Maybe we can call that the count. I'm going to call it count. We start at 0. Every time we find a k at one of these indices of A, we'll increment count. Whoa. All right. That's it. Any questions on this one? No? All right, number 7. Search for K and V. Do not use binary search because V is not in sorted order. This one is number 7. Oops. Let's find K and V and return the position of K and V. Otherwise, if K is not in V, then return -1. So let's look for K. Let's look at every index in V. So I is going to start at 0 and go up to and include v dot size -1. As soon as I reaches v dot size, we stop the loop. If we don't find K, it means we'll finish the loop. We'll run through the loop and never return it within the loop. So that means we didn't find it, so we'll return -1. We don't find it as we iterate across all the indices in V. We don't find K there. That means we finish the loop without finding K, so we return -1.
Oh, it's less than rows, then it's gonna be between. That's why I got mixed up.
So if we find K at I, we return I. So binary search. Do you want to do this again? Do you want me to do this now, or because we've seen it already, at least once? How many people want to see me code this up? How many people want to see me code this up? I only got 1 vote, so that's not enough. One's not enough. Okay, skip it. This is, you can go back and look at the video recorded session of this and watch how this is done again. All right, that's it. So we're in lab 9. Did I do sorting yet? Did we do sorting?
I didn't see sorting.
Did we cover this? Do we do sorting?
Yeah.
We did this, right? Yeah. Oh yeah, we were comparing the built-in sort with the with our sort. We noticed how much slower ours is, right?
Yeah.
All right, so we did sorting. This will be on the final. This is going to be asked on the final. Maybe I'll give it as a vector or an array. Maybe you need to sort in increasing order or decreasing order. So there's 4 variations actually.
Yeah.
Vector, an array, increasing or decreasing order. But it's easy. If you know one, it's easy to get the other one. All right, so the problem that I want to talk about today is this tic-tac-toe problem, but we're just going to continue where we left off last time, which is to build out this, what's it called again? 4 across? Connect 4. Let's review what we did already on that. So we declared a board. It's a 2-dimensional array of char. You don't have to do the tic-tac-toe problem with an array. You could. It's a small number of cells, or you could use an array. It doesn't matter. The connect 4 problem is a little bit more complicated because there are more combinations to make a win. In tic-tac-toe, there's fewer combinations that make a win. So we have this function that just displays the board. Whatever state, now this array here contains the state of the board. How many O's, how many X's are there? And every time that the main logic wants to display the board to the user, it simply calls this function display board. So we have that logic. We don't have it mixed in with our other code. We just have it there isolated. That this is a packet of logic. This function has a responsibility. It just displays the board. It doesn't do anything else. So we don't mix this logic with the rest of our code. And that's the main technique to keeping your program organized. It's called modularization. So we create these modules. All right. Here's a function that we haven't fully implemented yet. So this is in stub form. Is the move illegal?
Shouldn't goal be capitalized?
Huh?
Shouldn't that be capitalized or no? In goal or no?
It's just a great one.
This here?
Uh-huh.
No, this is an integer, and this is a
Oh.
column.
Okay.
You know, when you make a move in Connect 4, you have to choose a column. So basically, the user picks a column. So this is column 1, 2, 3. I'll pick column 3. And then the computer takes a column. I'll pick column 3 again. So that's basically, we're going to build this, but this has got a graphical interface to it. You know, you see some physics simulation in there, some bouncing of ball, and it seems to accelerate as it drops. But we're not we haven't been learning how to do that. So we're just going to provide an implementation that uses a text interface, this character interface. So as you can see, when a move is chosen, basically you just pick a column, so column 1. So is the move illegal? So we can flesh this out just a little bit, and it won't be complete. If the column is less than 1, or the column is greater than 7, then return true. It is illegal. You know, here's another thing about this, and then we have to check. You know, maybe the column is full. Okay, if the column is full, let's go ahead and do that. If the column is full, what does that mean? The column is full.
There's no way to place it there.
So we have 7 columns here, and 6 rows. So this is like the matrix here. This is, what position is this in our code? This is board of,
First column, row 6.
this is row 6. Is that how we did it? I think that's how we did it. This is row 6, this is row 0. And so we drop things down. So if there's anything, it's a legal move if there's a space in row 0 of the given column. So that's what we need to check for. I mean, that's one way to do it. There's other ways to do it.
Bless you.
So if the board of row 0 for column call, if it doesn't equal a space, then return true. It's illegal. That's how we were doing it. We were putting 3 different types of things in this matrix. So we have board of I, j. If this equals space, it means it's an available space. If there's an X in there, then that's we'll call it a player piece, like that. A player move. What would you call that thing? Or if it's an O, and it's the computer's move. So here, we're using X's and O's. Here, the player is red and the computer is blue, but we're using X for player and O for computer. We could use P and C. Is that easier? Player and computer? X and O is all right? Okay. So in this given column, COL, if it's row 0 has got a space in it, then it is not illegal. Now here's the thing. You know, in writing, when you're writing English, you want to avoid double negatives, and you want to avoid negatives in general. So if you can write it in a positive, it's simpler. So isn't this a simpler function to look at? If instead of illegal move, let's say legal move. Is this a legal move? So if the column is less than 1 or greater than 7, then no, it is not a legal move. If there is not a space there, then it is not a legal move. Otherwise, it is a legal move. That's easier, isn't it? Now we don't have to think about the negation, illegal move. It's just a legal move. I think that's simpler. Also, we can also do, if this line is hard to sort of think about, you can do it like this. If the value there is an X, or the value is an O, then it is not a legal move. There's already a a piece there. There's already been a move there. Which one is easier to read? This one or this one? They do the same thing. It's just a matter of readability. See, this one has the advantage of being shorter, but it has a not operator in there. I want to take a vote. For those who are following, which one is easier to? One? How many people vote for one as the easier one? The more readable expression. How many people think line 2 is more readable? I think one has it. It's shorter, isn't it? Here we have an or operator. The only thing here is this the not operator. So I'm going to take this one out. But that's an illustration. There's different ways to write the code, and you should think about readability as you're writing. So we just changed some logic. In fact, I think we fully implemented this. And we did change it to legal moves. So we're going to need to change this. Instead of when it's time for when player move is called, we're asserting that it's not an illegal move. Now we're going to need to change that. It should just be illegal. And look how much easier that is. So player move shouldn't, in our mind, in our planning, see, I don't remember doing this, okay? I don't remember this at all. But now I can see, because of that assertion, I know that when we wrote the code, we wrote it in such a way that player move will only be called when column is a legal move. That's my documentation right there, that assert. So somewhere else in the code pays attention and will not call player move if this column value is illegal. So this not only does it check, it catches a logic error, but also provides documentation, these assertions. So if it is a legal move, then we search downward to find out the first. We find the first spot that has something in it. How did we do that? Anyway, this is the logic. We went through that last time. We started at the top. Oh no, we started at the bottom and we looked for a space. Is that it? So the bottom is row 5. We started searching. So we're given a column. We need to put an X because it's player move. We need to put an X in this column. So we start in row 5 of the column. And we check, is this row 5 in that column a space? If it is, well, let's put the X there. And then we return. Otherwise, if there isn't a blank in row 5, then we're going to continue with the loop, which is to decrement I. So now we're looking at row 4. So we're going up. Now remember, this is row 0, row 1, row 2, row 3, row 4, row 5. So row 5 is the bottom. So first we check to see if row 5 has a space. If it doesn't, we go to row 4. Does row 4 have a space? Actually, this is a better example. Row 0 in column 3, row 0 does not have a space. So we check the next row. Does row 4 have a space? No. Does row 3 have a space? No. Does row 2 have a space? Yes. We're going to put it there and return. Now there's kind of like 2 coordinate systems here because to the user, we said this is column 1, 2, 3 like that, but actually I remember this now, when we read in the value from here, enter a column, when we read in this column number, we decrement it. So we convert the user's labeling system to our internal labeling system. So the user thinks that's column 1. But internally, because we're using an array, and array indices start at 0, we subtract 1 for whatever the user tells us, whatever column value the user tells us, we subtract 1 from it to get the column, the internal representation of that column. So this is the player move function. And we can always make a legal move here because of this assertion. If we can't, then the assertion will fail. Let's see, does that kind of run? I think so. Oh no, down here. Let's look at main here. So the first thing we do is we initialize the board. It should just contain all spaces. And then this is get and process user input. So there's 2 stages there. First, we initialize the board, and then we enter this loop where we get and process the user input. Initializing the board, we iterate through all the valid indices of board, and we set, for each of those pairs of indices, we set the cell to a blank or space. And then we enter this loop. This is called an infinite loop because the loop condition is always true. Well, we break out of it in here somewhere. No, we don't. It's an infinite loop right now. So it's an incomplete program. So let's think, what do we do inside this loop? This would be called the game loop, you know, or in a video game, this would be the simulation loop. This is the top level loop. All video games look like this, basically.
Computer.
We display the board, and then we prompt the user for input. You know, we clean the input by decrementing the column that the user entered. We check if it's an illegal move. If it's not a legal move, then we're just going to continue. We're going to go back to the top of the loop. That's what continue does. Continue means resume the loop. But if we pass this part here, then we can call player move. And then you're right, then we want, after the player moves, then we'll have the computer move. But let's see how this works. So enter a column, 1. So it didn't seem to work. Wait a minute. I don't think I can go into 1. Oh, I got the number wrong. See, that's not a legal move. And when I do 2, it goes into 2, and 7 is okay, but 1 doesn't do anything. So we got that, the change that we made today, we broke something. See, this column is not a user column. This should be our internal representation of the columns. So this should be 0, and this should be 6. So internally we label the columns from 0 to 6, not 1 through 7. As soon as the user enters in 1 through 7, we decrement it immediately. So we know that anywhere internally in our code that this column is not a user column, it's a programmer column. One, it works. 7, 8, nothing. We could print a message saying bad move. That's what we could say, right? Maybe that would be better. Let's see. You might be tempted to print bad move inside this legal move function, but that is not a good place to put it. That's called a side effect. You shouldn't. You should avoid side effects. So the legal move function just tells you yes or no. Is this legal or is it not legal? Don't do anything else. Just tell me yes or no. Is this legal or not? If you stick printing in here, you're now creating some confusion. The name of the function no longer represents what the function does anymore. The function just tells you, is it a legal move or not a legal move? It's not going to do anything else. So we would want to print down here. This might be hard to read, so we we could still improve it. We could say bad move, try again, and then pause, wait for the user to press enter. Please press enter to continue. We could do it like that to be more clear. But I don't want to spend any more time on that aspect of the code. I want to get to the sort of the meat of it, which is the logic, internal logic. All right, so now when the player makes the move, let's have the computer respond. You have a question?
Yeah. Before you do the display in the board and stuff before that while loop, don't you want to do your function to decide if the computer's going first or if the player's going first?
Yeah, here we could do that. We can add that logic. Did I ask for that?
Yeah.
In tic-tac-toe?
Yes. Because you want it before loop, right? You want it before the game even starts, so you can't be inside the loop.
Yeah. Let me add that later because that's kind of like frosting. Let's bake the cake first.
Okay.
That'll be pretty easy to solve. Here we'll just have the player move first, and then we'll add that variation to it, that extension. Can you remind me later at the right moment? Okay. All right. So after the player moves, then the computer moves. But if let's do this is player move, and I'm just going to do it like that. I'm going to keep it simple. Here's computer move. Nope, we didn't implement that yet. But here I don't want to take a column. Well, we could. It depends how we want to do it. We could keep it the same, actually. There's so many ways of doing this. Here we can get the next, we could do something like this. We could get the, we get a random column. We could do something like this. We can get a random column and then pass that into computer move. But I think what I want to do is just put that logic in here. I think that's how I want to do it. That's just a hunch I have, although it would work out the other way as well. So this computer move doesn't take an argument. So let's do a simple implementation where we're not challenging. We'll just pick a random move. So we'll declare an integer call, and we'll generate a random value. So it should be one of these columns, 0 through 6. Remember how to do that? Well, 6 is valid, right? So it should be mod 7. And then let's see, the best way to do this. Maybe what I'll do is,
Can you use pretty much the same if statement from the player move?
well, then the computer will always be moving to, it'll fill up the left-hand column first and go to the next one. It won't be very interesting. So the computer would play like me, watch.
No, after you pick your random column. Like,
Here's the thing, so we could pick a random column. Here's one way to do it. We could do it like this. So we could take our first guess, we could generate this call value, and then we say, well, if it's not a legal move, then try again. And then if that's not a legal move, then try again. And as soon as it becomes a legal move, then call is set to a good value. Well, there's only 7. I mean, how long is it going to take to get us to, if there's only one legal move left, then, it could take a little while. It's not wasteful. It's not great code. If you were going to change this and if the number of possible moves gets high, then this loop is going to end up taking a lot of time to run. So we're trying a lot of moves that repeatedly, like this code here could try the same bad column number over and over again. I mean, it'll work here. This will work. But it looks a little sloppy. You see the problem? So maybe I'm going to write a better routine. And I'll do it like this. I'll scan across all 7 columns and find all the columns that have legal moves. And then I'll add those index positions to a vector. And then I'll enter another loop, then I'll pick a random index position in that vector and use that as my column. Let me show that to you. So here's the, these are the legal moves, or the open columns. uh, and so I is going to be a column value, but actually we're using J for columns, aren't we? So let's just stick with J here. And there are 7 columns. So if J is a legal move, then append J onto the open columns vector. And I'm going to put in an assertion here. This open columns vector will have a size greater than 0. So I'm assuming that when we call a computer move, that some other logic is checked to make sure there's some available move. So now we have a vector of some size that has at least one legal move for the computer to take. So let's pick a random entry from that vector. So this is the random entry here. The random index. What do I mod by? Anybody following? I probably lost everybody here.
Yeah. Is it still 7?
No, because open columns may have 1, 2, 3, or 7 available positions. Yeah, that's it. You got it. Very good. The size of open columns. So that gives us, a random open column. So this code avoids the problem I talked about before. Now, once we have this, actually, I'm going to go back.
Is it 6 columns and 7 rows, or 7 rows and 6 columns?
It's
7
6 rows and
rows,
7
7
columns.
Okay,
That's 3, 4, 5, 6, 7.
okay, because then your J, if for int J is, or J is less than 7, that means you're only going
Well, our numbering
0 through 6.
0 through 6, yeah. 7. Now I can see. Now I'm gonna change things around again here, because this player move. I'm going to change this to just move. And I'm going to pass in the player or the computer. What would that be? The opponents? Or it should be, I'm not sure. Maybe that's, if I call that player, that's confusing, isn't it? The computer is a player and the user is a player.
I think I just like player and computer move.
I'm going to just call that the symbol. Right, that's easier. So here, instead of writing an X there, we're going to write the symbol. See, now I can reuse this function to move the player and the computer. So the player comes up with a column, we call this function. The AI comes up with a column for the computer to play, and we're going to call move to do that.
So for the tic-tac-toe, do you want the computer to have some sort of AI for it? Like making it.
No, you can make it,
or-
you can have it take a random cell. That's an AI, just picking a random cell. That's all we're doing here, is we're picking a random column. So that's, I think for the tic-tac-toe problem, you can use the same type of AI here, which is simply pick a random move. Here, we're picking a random column. In the tic-tac-toe problem, it's picking a random cell. It has to be an open cell. You can use that same process I showed you here. You can collect all the open locations and then randomly pick one of those. So the computer's not picking the same location over and over again. Yeah.
In the computer move section, what is that if statement supposed to be? In that,
This one here, that one?
below that
In computer, in void computer move,
Down,
down,
keep going,
keep going down,
keep going.
in there, where
Right,
it
one
says
down,
if.
one more, down, down. Right there.
He's saying, what does that if statement mean?
Oh, if,
I'll sing it.
yeah, I didn't do that right. It's bugged there. So if we're scanning across all 7 columns. We want to pick one of those columns for the computer to move, right? So we're going to look across all 7, and for each one that is presents a legal move, we're going to add that column index to our open columns vector. So when we're done that loop, the open columns vector will have all of the indices for the open columns. We'll have all of the possible moves that the computer can make. So in the next line, we pick of all those, we pick a random value from that vector. You know what, we have 5 minutes to go here. Let me try to bring this to a conclusion. It won't be done, but we'll finish it next time. So we changed this move. So we'll have the computer moving today, we'll see. So we want to move, we'll pass in an O, and the column that we picked. Now we need to fix this code down here. We no longer have this function, it's now called move. We're going to pass in this X symbol. Let's see if that works. We need to include vector. That worked. Enter a column. Is it going to work? I don't think it's going to work. Look at that. Look at that. Oh, it's picking the same one. No, it's not. It is not picking the same one. Oh, we're having a real game here. Look at that. So now we have, well, we're not checking the win conditions. And when we fill up the board, we're not testing for a tie. We have to test for a tie. And each time one side makes a move, we have to check the win condition. Does the entity that just made a move, do they now win the game? And if not, then continue. Also, did you win the game? If it's yes or no, also, is it a tie? So we'll finish that next time. All right, that's it.
Can you go back to your code? That last little part you just added, please.
Aside from finishing this code, are you gonna go like review or gonna answer questions or?
Yeah.
Can you go all the way to the bottom, Professor?
All the way to the bottom?
Yeah, because you added C at the very end there. Instead of clear move, you